Hello, this is Tim Lichtenberg from the University of Oxford, and in this talk I will give a short status update about the Large Interferometer for Exoplanets mission concept. So, within the exoplanet community, in the long run, we have several mid and long-term goals. Three of them are listed here. First is to assess the atmospheric diversity of specifically rocky and terrestrial exoplanets across the closest star systems. Then assess the potential habitability of these worlds in terms of markers such as, for instance, their climate diversity and their specific climates. And then three, search for potential biosignatures across these worlds. Now, how do we do this best? In an ultimate world, what we would be able to see is something like this, an image like the pale blue dot, which directly enables us to actually probe the atmospheric signature of that world from the emitted light of the planet itself. This can look like this, here showing the geometric albedo of the planet in UV optical NIR wavelength and mid-infrared wavelength, showing that these different wavelength regimes offer different views of the spectral signatures and absorption bands of these worlds. Now, how do we do this at present day? At present day, the exoplanet community is very focused on indirectly detected planets via transit and radio velocity surveys. But we have detected also a few directly imaged planets so far. This is shown in this iconic video by now, showing the HR8799 system. In this specific video from Keck, observed by Keck in 3.8 micrometer. But these are very massive planets, 5 to 12 Jupiter masses at very large orbital separation, 16 to 72 AU. How can we get closer? How can we get closer in? How do we actually breach this and ultimately are able to observe and characterize terrestrial-like exoplanets? So this is what the current and near future looks like. So today, with the 8 to 10 meter class telescopes and the recently launched JWST, we cannot directly detect terrestrial exoplanets, nor can we characterize their atmospheres. This may slightly change with the extremely large telescopes in a 10 plus year time frame. So we may, if we are lucky, we may get the signal and be able to characterize Earth-sized exoplanets around the very nearest handful of stars. But if we are unlucky, or these are not the planets that we are actually looking for, then the more long-term future commitment should be, or can be, to make this a reality, to actually invest into a flagship, space-based flagship missions in a 20 to 30 year time frame, because this is the approximate timeline for these large-scale missions. So what are the challenges for this? The main challenges are, first of all, related to the spatial resolution. We need to separate the planet from the star, and that is a very, very small distance on the sky. So this plot on the right hand side shows the distance in AU versus spectral class of the star, stellar temperature here in K, and this shows the habitable zone across these stellar regimes. And this is to illustrate the spatial resolution with 30 to 40 meter class, the extremely large telescope for a star 10 parsec. These can really only observe beyond this distance here. So at 1 micrometer in reflected light, we are basically cut off from the habitable zone of M-star planets. And at 10 micrometer, which is the peak of the thermal emission of terrestrial planets, we are cut off from the habitable zone across all stars that we are essentially interested in, M, K, and G stars. So we are blind to anything that is inside this distance here. This is unfortunate because within 10 parsecs, which is just realistically really the distance that we will be able to access within our lifetimes, we have about 64 FGK stars and about 280 M stars. So we would like to be able to properly assess these planetary, stellar, and potentially planetary systems. Now, the second challenge comes from the contrast between the sun, or the star, and the respective planets, because the planet is so much fainter than the star itself. And this is illustrated in this image here. So this is for a Sun-like star, the flux, and this is for an M-type star, the flux. Here's the Earth. And so you see that in a reflected light, the contrast difference between a Sun-like star and the Earth is about 10 to the 10, and in thermal emission it is 10 to the 7. And for an M star, this is 10 to the 8 for the reflected light, and 10 to the 6 for thermal emission. Now, what this really brings up is two different strategies, the two bumps that you've seen in the in the image before. The two different strategies of the peak are really probing the peak of the reflected light or the peak in thermal emission. And so our US-American colleagues in the NASA 2020 Decadal Survey have proposed various concepts for the future, for instance the LUVOIR and HABEX concepts that aim to do this type of science in reflected light. And we in Europe currently assess the potential for a space-based mid-infrared instrument that is probing the thermal emission peak of terrestrial exoplanets. So what really is the idea behind the Large Interferometer for Exoplanets initiative? It is to develop the scientific context, the technology and roadmap for mid-infrared space mission to investigate the atmospheric properties of a large sample, really 30 to 50 on that order of terrestrial exoplanets, and really to investigate the diversity of planetary bodies, assess their habitability, and search for potential biosignatures in exoplanet atmospheres. How does this look like from a technological perspective? The live mission concept is a space-based formation-flying mid-infrared nulling interferometer, this as shown on the right-hand side. This means in a fiducial setup, 4 collector spacecraft that are separated with tens to hundreds of meters. In this specific case that is shown here, the long baseline would be something between 60 to 600 meters and the short baseline 10 to 100 meters. And the light is combined in a beam combiner spacecraft, and covering the wavelength range between 4 to 18.5 micron and spectral resolution of R equals 50. But all these values and fiducial setup that I describe here are really just the fiducial current our current thinking, and we are assessing this with regards to scientific output and technological requirements. Okay, what type of exoplanets would such a mission actually be able to detect? This is shown here. In order to demonstrate this can be a standalone mission, not dependent on any output on any surveys that come before it. We basically assessed the potential hypothetical detection yield, similar as was done as for the LUVOIR and HABEX concept in the NASA 2020 Decadal Survey. For that, basically we used a Monte Carlo simulations based on Kepler statistics within 20 parsecs, assuming a 2.5-year total search phase and 4 2-meter apertures for the instrument, and a 5% total instrument throughput. And these are the numbers that came out of this. This is the mean number of detectable planets, excluding Jovians, subdivided into rocky and super-Earth, sub-Neptunes and sub-Jovian planets. These are the numbers for the LUVOIR I and B concept. This is the number for the HABEX concept, and these are the numbers predicted yield estimates for two different search strategies with live. What are the differences here? So this first of all shows you that this specific survey strategy is comparable to the LUVOIR A concept. Now, what are these two different strategies? You can either maximize for the total number of detected exoplanets by equally searching all different, for instance, distance regimes, or you can try to maximize the number of rocky habitable zone exoplanets. And for simplicity here, let's just look at this bottom plot. This shows the detectable planets was subdivided by different planetary classes. For instance, rocky planets within the empirical habitable zone, which we expect to find on the order of 43 planets with this specific search strategy. And then 20 exo-Earth candidates. This is a sub-fraction of this number here. And about 150 rocky and super-Earth exoplanets. Okay, one of the main findings of this thing here, this specific paper shown on the bottom right here, was that just with such a search phase, we could very well characterize single planets with already just one observing epoch. And so just during the search phase, the average error on the temperature, on the injected, of course, hypothetical planet population, the average error on the derived retrieved temperature of these planets is 10%, radius 20%, and the separation from the host star about 1 to 2%. These numbers, of course, can be significantly improved by specifically characterizing a single individual planetary system. Now, how does life fare with regards to the discovery space with known nearby exoplanets? This is shown in this plot. This is the installation or insolation relative to the Earth. This is the radius of the given planets, and the blue dots are the already known exoplanet census within the nearest neighborhood, within 10 parsec. We know about 60 planets at present day. And the red contours are the predicted live detection yield. So really clustering in this phase space here, specifically showing that the planets that are known so far could be very well characterized with the live mission. Now, the mid-infrared, the point here is really that the wavelength range chosen or covered is really covering the peak of the thermal emission of temperate terrestrial exoplanets. And it features major molecular constituents and major absorption bands of very interesting molecules, such as, for instance, methane, ozone, or nitrous oxide. So what is the point about the mid-infrared wavelength? What is really the advantage here in comparison to different concepts, let's say? So a mission that operates in the infrared can directly constrain the pressure-temperature structure of the planetary atmospheres. It has multiple atmospheric absorption bands, specifically water, carbon dioxide, and carbon monoxide, and it can constrain the collision-induced absorption from nitrogen and oxygen for planetary atmospheres that are dominated by these gases, for instance. It is sensitive to potential biosignature absorption bands, for instance, ozone, methane, nitrous oxide, phosphine, ammonia, and isoprene. And last but not least, it can directly constrain the effective temperature of the planet and provide access to their radii. So it is very synergistic, for instance, with radial velocity measurements of the nearest stars. Number of studies have been accepted already regarding the live mission concept. Papers 1 to 3 and 5 and 6 have been accepted and are available on the archive. Paper 4 is currently under review, as are paper 7 and 8, and paper 9 is currently close to submission. Further papers are under active investigation, and we are working on many more papers within the individual working groups of the live mission concept team. Now, how is there a chance for a mission like live to ever fly? The answer is yes, luckily. That is because within the ESA Voyage 2050 timeframe, which is a similar exercise as the NASA 2020 survey, but with a different timeframe, in the report that came out of this, it was identified that the characterization of the atmosphere of temperate exoplanets in the mid-infrared should be a top priority for ESA within the Voyage 2050 timeframe. And specifically that to measure a spectrum of the direct thermal emission of a temperate exoplanets would be an outstanding breakthrough that could lead to yet another paradigm shift discovery. So what leaves us this with? It leaves us with this rough roadmap for the future space exploration, specifically exoplanet exploration, where we are currently right here. Cheops has been launched, JWST has been launched. Within the 2020s, with regards to space-based observatories, we're looking at the launch of Plato in 2026 and Ariel in 2028. And then a long gap, actually, because the missions that are supposed to launch in 2030 to 2040, these calls for the F-class and M-class missions are already closed, and no exoplanet mission candidate has been proposed nor selected within the ESA framework. This leaves us with missions from the 2040 onwards, and very specifically the L5 class slot is open for this, and live could be a potential candidate for this slot, which is what we're actively investigating and working toward to provide ESA with tangible science goals and ready technology to deliver these ambitious goals. So what does this mean? As a summary, LIFE is a European-led initiative for a large future exoplanet mission. The science team has already been recognized as a potential candidate for an L-class mission within the ESA science program. We are working actively on research and development for critical components and subsystems. They are starting to ramp up across Europe, and we're working towards a systematic and broad approach with more partners to carry out concept studies. We're very interested in collaborating with you, so if you're interested and think this is worthwhile and you believe that you could contribute to such a mission, please do reach out to us. Very importantly here, LIFE is not a closed club. We are open to everyone who is interested and has a professional interest and collaborative motivation to do so please reach out to us. You can find all the information about LIFE on livespacemission.com. You can sign up for the newsletter and contact the team at via live@phys.ethz.ch, and you can follow us and interact with the LIFE Twitter account at live_telescope. And with that, I want to leave you with a final video presentation that we hope brings the excitement of the potential science that can be done with a life-like mission directly to you. Thank you so much for your attention.
Are we alone in the universe? LIFE, the large interferometer for exoplanets, is designed to address this question by collecting infrared light from distant worlds. We know of thousands of planets orbiting other stars, and LIFE will help us understand their diversity. For the first time, we will be able to tell if some worlds are similar to Earth. With atmospheres containing molecules such as methane or oxygen that may indicate biological activity, our team is dedicated to discovering if life beyond Earth is rare or a widely spread outcome of cosmic evolution.